The ancient Greeks had known about the whole numbers, of course, the numbers 1, 2, 3, 4, 5 and so on that were used for counting, but it was obvious to them that a host of in-between numbers were needed for measuring everyday things like hypotenuses and circumferences and most other quantities. For this they used ratios of whole numbers. For example, the length midway between 1 and 2 could be represented by the ratio 3:2, meaning that if you took two segments of the length in question and laid them end to end, you would have measured out a length of 3 units. Other measurements might be a bit more complicated, but it was believed that if you laid enough of the same length end to end, you would eventually come to a whole number. In this diagram, an ancient Greek mathematician is attempting to use the diameter of the circle to measure the circumference. He sees that 7 circumference lengths is about the same as 22 diameters, but no matter how careful he is, the 7 circumference distance always seems a tiny bit more than the 22 diameters. He realises the ratio 22:7 is not quite right, and so he is on a quest to find the perfect ratio. In this picture, an ancient Greek mathematician is contemplating an isosceles right-angled triangle made out of sticks. Pythagoras had confirmed that the long side should be the number we would represent as square root of 2, because 1 squared plus 1 squared equals 2. The question is, how many hypotenuses laid end to end will make a whole number of sticks? From looking at the sticks, it is clear that the hypotenuse is longer than 1 stick but shorter than 2. Perhaps the correct ratio is 3:2. On rearranging the sticks, we see that 2 hypotenuses is just a bit less than 3 sticks. The ancient Greek has found a square grid of floor tiles with which to experiment. He finds that 5 hypotenuses is very nearly 7 sticks, but this time the 5 hypotenuses are a tiny bit more than the 7 sticks. So the ratio 7:5 is good, but still not perfect. A better ratio is 17:12, but 12 hypotenuses measure out a distance that is not quite 17 sticks. A still better ratio is 41:29, and even better is 99:70. But while each of these is closer than the one before, none of them represents the precise length of the hypotenuse. Someone, in the time of Pythagoras or a little after, made an awful discovery. The hypotenuse in an isosceles right-angled triangle could never be measured by a ratio involving the legs. As we would say, root 2 is irrational. Plato, writing some years after the event, says the discovery was very disturbing. It was realised that ratios of whole numbers were not sufficient for every kind of measurement after all. Some stories say the discovery was made by Hippasos of Metapontum, a member of the Pythagorean Brotherhood, and that he was drowned, deliberately or accidentally, during a sea voyage for revealing the terrible fact that some measurements cannot be expressed as ratios of whole numbers. However, no one knows for certain how this momentous discovery was made, or by whom. There is evidence in Aristotle that the proof in the case of measuring the diagonal of a square by the sides involved thinking about odd and even numbers. The proof of the irrationality of root 2 that is often shown to high school students is of this kind. It is not the simplest of the many proofs that have been devised, but it has antiquity in its favour. To conclude this part of my talk about irrational numbers, I will run through a version of the odd and even type of proof. Consider a right-angled isosceles triangle. We wish to measure the hypotenuse in terms of the legs, and in the manner of the Greeks, we intend to use a ratio of integers, a is to b, which says b lots of the hypotenuse should be the same as a lots of the legs. We can assume that a and b are not both even. If they were both even, we could halve both numbers and obtain an equivalent measuring ratio with smaller numbers. In effect, we are using the leg length as our unit of measurement. If the hypotenuse has length h, we are saying, according to the measuring ratio, that b times h equals a times 1. But then b squared h squared equals a squared. Now Pythagoras tells us that h squared equals 2, because the legs each have length 1, and 1 squared plus 1 squared equals 2. So we can write a squared equals 2b squared. This means a must be an even number, and since a and b are not both even, b must be odd. So we can write a equals 2m, where m is some integer. Then a squared equals 4m squared, and so 4m squared equals 2b squared. After cancelling a 2 from both sides, this says b squared equals 2m squared. This means b must be even. Now b appears to be both odd and even, which is impossible. We must conclude that there cannot be a ratio a is to b that measures the hypotenuse in terms of the legs. This all seems a bit complicated, mostly because it is done in terms of geometry. These days we would use plain numbers without any necessary connection to the lengths of the sides of triangles, and we would produce a simpler looking proof. In the next part of this talk, I will approach the existence of irrational numbers in a very different way, by introducing some 19th century mathematics, specifically the work of Georg Cantor.